Good day everyone, I am James Cruz together with
Ashley Del G. Bontia.
and we are the Wizards of Group 13. Today, we are going to present the relative strengths of acids and bases.
First, what is our learning objectives? Number 1. Define what is meant by the strength of an acid and a base. Number 2. Differentiate between strong and weak acids and bases in terms of ionization or dissociation in water. Number 3. Explain how the acid dissociation constant Ka and base dissociation constant Kb indicate acid and base strength. Number 4. Apply the concept of relative strength and identifying conjugate acid-base pairs.
So what exactly are acids and bases? Acids are substances that donates hydrogen ions, while bases are substances that accepts the hydrogen ions or releases hydroxide ions. Strengths depend on how completely they ionize in water. Now, strength of acids. Strong acids are characterized by completely ionizing in water, meaning their reactions with water is essentially 100% complete. Example, hydrogen chloride is broken up and completely dissociates into hydrogen ion and chlorine ions. Strong acids have very large Ka values. Now, weak acids are acids that only partially ionize in water. The conjugate base of a weak acid is strong enough to compete with water for protons, so the reaction does not go to completion. A weaker acid has a smaller Ka values. Strength of bases. Strong bases. These bases react completely with water to form hydroxide ions. Soluble ionic hydroxides like sodium hydroxides are considered strong because they dissociate completely. Examples: sodium hydroxide, potassium hydroxide, and calcium hydroxide. Now for the weak bases. These bases, when reacting with water, produces only a small amount of hydroxide ions. Their conjugate acids are strong enough to compete for hydroxide ions. Now, to further understand this concept, we have prepared a video presentation for you guys to see.
Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic, our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metals. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging two main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, That is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, the base, shop at the same time, their net effects on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules. Which is more than I can say from wah wah.
Now that's done, let us proceed to the lesson.
Let us proceed to the factors affecting the strength of acid. 1. Conjugate base stability. A more stable conjugate base means the acid is more likely to donate a proton, making it a stronger acid. Number 2. Polarity and bond strength. For oxyacids, increasing the electronegativity of central atom or its oxidation number increases acidity because it weakens the OH bond. For hydrohalic acids, strength increases as the atom size increases down the periodic table, which weakens the XH bond. Number 3. Ionization constant or Kb. Just as with acids, a stronger base has a larger Kb value. Number 4. Reciprocal relationships. A strong base has a weak conjugate acid, and a weak base has a strong conjugate acid.
Now, let us proceed to the conjugate acid-base pair. So what exactly is a conjugate base pair? There is an inverse relationship between the acid of a conjugate base-acid pair. The stronger the acid, the weaker its conjugate base. For example, hydrogen chloride is a strong acid, therefore its conjugate base pair is chlorine, which is a very weak base. Now, how do we exactly measure the strength of acid and bases? Ka, acid dissociation constant. Larger Ka equals to stronger acid, while Kb, base dissociation constant, means larger Kb equals to strong base. Example in real life. An example of a strong and weak acid in real life is stomach acid and vinegar, while strong bases and weak bases in real life are drain cleaner and ammonia cleaner.
Summary: strong acids bases fully ionized, weak acids bases partially ionized. Acid strength and base strength are inversely related. Use Ka, Kb, pKa, and pKb to compare strengths.
That's all.
Salamat! Just